Good morning, everyone, or at least it's morning when I'm making this video. So things are going to be a little interesting the rest of the semester, actually. Um, so I'm going to be making some videos, and Professor Flippo is going to be making some videos regarding some of the lab work. Now, we encourage you for the simulation portion to actually do the simulations yourselves. I mean, you know, we're not requiring that you do that because we understand that if you're at home, you're not necessarily going to have access to the software. Although, as we have posted on our Blackboard sites, there is a way to get a free student version of this for your computers. The only restriction is that you have to have a PC computer. It will not work on Mac unless you boot Mac in a Windows operating system. So what we're going to do here is we're going to do a simulation that's called an AC sweep. We're looking at filters here. We're looking at low pass, high pass, and band pass filters. And we want to be able to see if the filters are working the appropriate way. So this first simulation is a very simple filter that we're going to be looking at here. So let me go ahead and create a little directory here. I think, do I have one yet? Cadence 3650, create directory, and I'm going to call this filter 1. And we're going to call this a passive filter, because that's what this lab is about this week, is passive filters. There is such a thing called active filters, and we will talk about the difference between passive and active filters. So we're going to create a blank project. Everything until we actually simulate is going to be the exact same as what we've done before. Now the circuit is very simple. It's just a simple resistor and capacitor. This is what's called a first order passive filter. And so we're going to go ahead and place the parts. As a side note here, this is not something that is critical, but sometimes people like to, install all of the libraries on their computer here, and I don't necessarily like to do that. I like to just have the libraries installed that I want to. And remember, you can always add a library by just clicking on that, and if you're not in the correct directory, I'll bring this open here so you could pause it. It's going to be Cadence SPB 17.2 Tools, Capture, Library, PSpace. So to find all of the libraries is a little bit challenging, but this is where all of them are. And that's where like the analog one is, which of course contains our analog components, the sources, which honestly for this simulation you only need analog and you only need source as far as the libraries. So I'm going to go here to analog. I'm going to pull out a capacitor. In a second here, there we go. And then I'm going to pull out a resistor. And now I have to put a voltage source, but this is very important here. There's lots of different types of voltage sources, and we need to choose the correct one. So we've been using like the DC voltage source for obviously DC power, but this is not a DC source. We're looking at an AC signal. Now, the other one that we've also used is this V sine, which creates a sine wave. We don't want to use that one either. Honestly, what we want to use is there is one here called VAC. And so I'm going to look at VAC here and put it right there. And then I also, before I make any connections, of course, I have to put a ground in. So I put G for ground, and then I'll just place my ground. And then let's go ahead and change these parameters here. Honestly, I'm not even doing a design per se. I'm just picking some random ones to show you how you could do this. So let's have this be 10K, and we'll have this one be 0.1 microfarads. We'll see what happens when we get this. I just picked random values. I haven't even computed anything at all for this. And then, of course, we need to wire this up correctly. Now, one thing I want to talk about here is when we're analyzing circuits or filters, you often want to make sure this is 1, because what we're often looking for is what is called the transfer function. In other words, what's the output over the input. And I'll just go ahead, there's not a need to do this. I'm just going to say output, which is right here, and then input, which is over here. So my transfer function is h, and at j omega, which is the same thing if you've done Laplace transforms yet, which is h at s, which is just v, the output over the input. And I'm putting that as just output over input because it doesn't have to be voltage over voltage. You could actually have the output current over the input voltage. That's a type of transfer function. Now, the ones we're going to look at in this course are always going to be the voltage. So we're going to look at the output voltage over the input voltage. But by leaving this at 1 volt AC, well, now your denominators just become 1. So you divide by 1. So really, the output now is simply your transfer function. So if I had changed this, though, to 2, well, then whatever my output is, I have to divide by 2 in order to get my transfer function. So it's very useful just to leave this as 1. We don't want any kind of DC offset, so you leave that at 0. The next thing we have to do, of course, is set up our simulation profile. Now, in some of the videos or in some of the labs, you may have been typing transient. And that was because when we say transient, we're looking at the circuit with respect to time. Now, in this case, I'm going to go ahead instead and say frequency, because we're not interested in how the circuit behaves with respect to time. We're interested to see how the circuit behaves with respect to frequency, meaning that I'm going to be in steady state for all of these things, but then what I want to see is like, well, when I change the frequency of the input, what happens to the output? So my little settings have come up here. So I have to change what it is I'm doing. The analysis type here, see it says time domain transient. Well, if I pick it up here, there's 4 choices. The kind of obvious one, in my opinion, would be the AC sweep or noise, because we're again wanting to see how this thing is changing with frequency. So if I select AC sweep, I can see here now I got an AC sweep. We actually always want to do logarithmic. You don't want to do linear. We always want to plot these in a logarithmic format, and that's because the frequency ranges, we go from like 1 hertz maybe up to 1,000 megahertz. And if you did that linearly, the graphs would look really weird. But if we do it logarithmically, the graphs look a little bit nicer. Now we have to put a start frequency. Never put 0. 0 is DC and will often cause the simulation to crash. So you could start at 1 hertz or even 0.1 hertz or something like that. I'm going to start at 1 hertz, and I have no idea what this one is going to be like, so I'm going to go all the way up to 100 kilohertz. And then points per decade means like, well, how many points am I going to simulate per decade? And a decade would be, of course, frequencies from 1 to 10. Now when we're talking on a log scale, though, it's putting 50 points in that decade. It's not putting 50 points spaced out linearly. It'd be putting 50 points in on a log scale base between 1 to 10, and then another 50 points between 10 and 100, another 50 points between 100 and 1,000, so on and so on. So 50 points per decade is a pretty standard one to use. So I'll go ahead and do that. I mean, you can do more. That will just make the simulation go longer. You can do fewer, but sometimes if you do too few of a points, you don't really get to see what behavior is going on. All right, so it's all set up. And now I'm just going to go ahead and simply do a simulation here. So I'm going to run it. And I get an output, and of course there's nothing on my output. And my computer at home, I have a black background. So I can go ahead and plot my output here. And if I look at it, I can see, okay, well, this starts at 1 volt, goes down to 0 volts, but this doesn't look anything like the bandpass. Well, I guess it kind of does look like some of the low pass, like, oh, this looks like maybe here's the low pass frequency and it scales all the way down here. But we're not plotting in the correct area here. So what we always want here, we always want the decibel values instead of straight voltage. And to do the decibels, the actual formula to do the decibels here would be, if you want to talk about dB, volts. So if you have something in voltage and you want to get the dB of it, you would do 20 log base 10 of, and it's going to look a little weird here because of the things. It's hard to see in here, but I have vertical lines around the h at j omega. That means it's the magnitude. You might want to say absolute value, but it's technically a magnitude because we're talking about complex numbers. So it's 20 times the log of that. Because, again, we're in a log scale, so it would make sense to look at our data in a log scale as well. So that's what we have to do to compute it by hand. And there's a reason why it's 20, which in another video to prepare for the lab, we talked about that. But fortunately for us, we don't actually have to sit there and do this computation. There's two ways you can do this. One here is that we can say, okay, well, I'm going to just delete this trace here. And I'm going to do plot or trace. I'm going to add a trace. And I'm going to take the currents and power off. So I have this voltage output. And we know that that's my transfer function because my input is simply 1, which is nice. But what I can do here is, I don't want to plot that, is there is right here an expression called dB, which means convert it to decibels. So if I do that, the graph now looks much nicer as far as this looks like what we would see as far as a low-pass filter. And again, this is a first-order filter. Higher-order filters would have a more sharp turn down. They would look like turning down a little bit sharper like that. Now, as soon as you make higher-order filters, you've, of course, introduced the complexity. Now, this is always gets people here at first, is 0 decibels refers to that there is no gain. 0 decibels is not multiplying by 0. Because you think if the output is the same as the input, then V out divided by V in is 1. And the log of 1 is 0. So 0 decibels means that the output's equal to the input. Then minus 10 and then minus 20 means that we're not getting as much of the input on the output. So that means here, for instance, minus 30 decibels, that means we're not getting very much of the input signal on the output. In other words, we're filtering it off. Now there is another way. I'm going to go ahead and delete that probe, and I'm going to go ahead and delete this trace. There is another way to do this as well. You can only do this once you've simulated the circuit, though. If you go to PSpice, Markers, Advanced, there is a dB magnitude of voltage marker. But you can only select this once you have simulated the circuit. If you try and do this before you simulated, this will be grayed out. You won't be able to select it. And if I do that and select it and put it there, we can see that it also does the exact same thing for us. Now, one thing we're always interested in is what's referred to as the cutoff frequency, which is the minus 3 dB point. And the reason we're interested in the minus 3 dB point is that is what was considering half power. That's where the output signal is at half power of the input signal. So that's why we're interested in the 3 dB point, is because we've cut the signal's power in half at that point. And then another minus 3 dB, you'd cut in half again. So in other words, it'd be 75% of what it would be originally. Okay, so then how do we do that? Well, we're going to evaluate a measurement. And now we have to be a little bit careful here. So if we look here, we have to first tell what kind of filter it is. Well, it's a low pass filter. We can see low frequencies are getting through, but it says 3 dB. I'll just go ahead and do it right now to show you what the error is. If I just simply put V out in here, it actually, oh, in this case it does. Sometimes you get an error here. Low pass filter, this is actually correct. This is 158.7 hertz. Sometimes you need to convert it though to decibel rating. So let's go ahead and do that again. So we're going to do cutoff low pass, and then what I'm going to do is dB of the output. And you see you get the same number. I always like to do the second one here that I've done because sometimes this one does not work properly. So I always like to do this one just to be safe. But we can see that we get the same frequency here. So the 3 dB cutoff for this random design that I created is 158.8 hertz. So in this lab that you guys are going to be doing, you're going to be designing a filter for specific frequencies, and then we would like you, if possible, to simulate them. You know, and if not, you need to communicate to either me or Professor Flippo that you aren't able to simulate it, and we will work with you on that. But Professor Flippo is probably going to be making some additional videos on how to do these frequency sweeps for filters, because we also have a high pass filter. We're going to be looking at band pass filters, and we're going to be looking at active filters as well. All right, so hopefully this has been a insightful video to you. I probably blathered on too long, but I like to talk. You all know that. So hopefully you've learned some things here, and we are going to continue on. And again, once you have your design for your circuit and you want to actually do the measurements, you need to email Professor Flippo or me, preferably me, because I'm going to be the one doing the measurements. My email is here, let me just type it out here. My email is, where's the text box? Right there. Is dwrumsey@indianatech.edu. So once you have your design for your circuit, you need to email me what your resistor and capacitor values are for your design, and there's more than one correct way to do this. And you need to email me that design, and then I will build your circuit for you and do the measurements and send those back to you so you can write your reports. And then also we will want the simulations as well, and we would prefer you to be doing these on your computer, but if you cannot do that, again, please contact either me or Professor Flippo. All right, so I will end the video here now for certain.